Hello everyone. My name is Chang, Hoon, and I'm faculty from the Western New England University. The school is located at Springfield, Massachusetts. It's a 2-hour driving from here. So what I'd like to talk about today is not in detail about the concrete, but before the aggregate morphology used for the cement-based material. So first, I'd like to just thank you very much for my colleagues at my school, as well as a colleague at the Florida International University. Technically, this project was sponsored by the NSF, and also the part of the funding came from the University Transportation Center program. So technically, our research was just motivated by the simple test. We made a 2 concrete cylinder, and then for making those concrete, we used 2 different shapes of aggregates. The one is crushed aggregates, which is a little more angular looking, and the other is a river aggregates, more the rounded shape of aggregate. Once we loaded some of the pseudo-cyclic loading to those specimens, then we got the higher peak strength from the specimen with the crushed, and we got a little bit more lower. However, clearly we can see that the stiffness degradation because of the cyclic loading is quite lower when you use a round shape of aggregates. So I believe that this is not a really new item of the topic. Instead, we somehow understood that we are using crushed aggregates, then that's going to produce more surface area. That's why we can expect a greater quantity of the bonding between the paste matrix and the aggregates. So that's why probably we're going to get the higher peak strength. On the other hand, if you use a rounded aggregate, maybe you can minimize the stress concentrations at the corners of aggregates. So that's why probably we are going to have a little bit of the higher resiliency of the property. So that is not a really new topic. However, when we just try to consider quantitatively the shape of the aggregates in the mixture design of the concrete, we had a little bit of the issue. One issue is that we just wanted to define the shape of aggregates. Then if we just go to the literature, we found out the bunch of the 2D morphology parameters, the so-called the sphericity, how the shape of the random particle is going to be close to the circle. That is the idea of the sphericity. And the other is the roundness. This is a little more, a few order of the magnitude smaller scale of the shape. But if you really see the mountains and valleys on the surface aggregates, how the shape for those kind of things is going to be a whole story about the roundness. And regularity is just nothing but the weighted average of the sphericity and the roundness. But also, if you really want to see the 3-dimensional morphology parameter, there's not many. So we just found out the one from the paper published a long time ago, 1932. Then we just digging a little bit of literature at that time. Then quite a number of the researchers worked on to define the shape of the particle or aggregate. So let me just talk about a little more details about that. So this is just the list of the 2D sphericity parameters. But probably, no matter what parameter you are using, the first step is you are just first feed the projected image into the rectangle or the circle. Then from there, you just calculate the area of the random shape and perimeter of it, or even you measure the dimensional length of it. You just compare those collective value with the reference rectangle and the circular. From there, you should be able to calculate those kind of sphericity. But actually, the ASTM D4791 is providing the method to measure the elongation of the aggregates by experiment. So that doesn't really use digital imaging processing. But nowadays, a lot of the digital imaging processing is advanced. So-called AIMS is one of the popular way to just characterize the shape of it. However, that is a so good method. However, we just found out a little bit of the thing. As long as you use project image of the particle. So let's imagine that some of the literature says that maybe 3 images is going to be enough, 5 images is enough. So there are some agreement about the number of how many images you have to use for digital processing. However, we just thought about what if you just put the one particle into the center of those point cloud and taking 1,000,000 photos. So this is just 100 samples of each particles right now. And calculate the sphericity of each particle. So technically, you can get 1,000,000 values of the sphericity. And you can get 1,000,000 value of the roundness. The question is that those values are going to be just close enough. So that is the question. So we just did just simple the analysis for that. This is what you got. So I believe that it's really hard to see that. First of all, depending on the different types of the sphericity, that you can get the different values of it. You expect that one. True. If you have two different shapes of aggregates, then you expect that the value might be a little bit different from each other. That is true. However, once you really take 1,000,000 of the photos and get the values, then all the values are somehow overlapped with each other. So that somehow means that if you are lucky enough, then you can differentiate the shape of the aggregate from the one to the other. But if you are not lucky enough, then it's going to be almost really, really hard to differentiate the shape of aggregates by using those 2D parameters. So that is something that we just got from that. So we just thought about, probably we need to propose a 3D morphology parameters, but actually there's not many available in the literature. So one of the possibilities is so-called the true sphericity proposed by the Waddell 1932. So that is just nothing but ratio of the surface area. So the A sub equivalent is that you first take the volume of the particle and then imagine sphere having exactly the same volume of it, then AEQ is the surface area of those fictitious sphere. And then the denominator A is a real surface area. However, even if he proposed that method, then in that particular paper, we couldn't find out any experimental value. Probably because in that era is limited to get the 3D model of the particle at the time. So the title of the paper was True Sphericity. However, most of the contents was about the 2D sphericity, which is the equivalent version of the 3D. But anyway, however, our research team figured it out that this true sphericity is pretty good the parameter model. However, it's not really sensitive to the elongated particle. So if you somehow have exactly the same volume of the particle, one is a sphere and the other is really, really long. But that sphericity, Waddell's true sphericity cannot detect elongation, differentiate those kind of two cases. So somehow we just proposed Marvel parameter. The name of it itself is somehow disliked by the reviewers somehow. But anyways, that is just nothing but you can measure the surface area and you can measure the whatever characteristic length and divide by 6V, then it's going to give you some kind of value, but that's going to be used for the morphology. So that is actually our idea. That can be anything. So it's not really the special. Instead, we just try the one of the morphology value, then we just try to use it. But benefit of using that form is that we can recycle the true sphericity, which is proposed by the Waddell, and highlighting L divided by DEQ, which is a term for emphasizing the elongated shape of the particle. So for doing that purpose, somehow we had to put, instead of putting the projected image into the rectangle or circle, we had to put the 3D model into those sphere. Sometimes we had to put the particle into the container box. So from there, we can just measure those parameters. But while doing this thing, the key technique is what we used was the structured light scanning. So you guys already heard about the 3D scanner, quite different versions of it. But once we use the laser-based 3D scanner, it takes a lot of time, and resolution also was not guaranteed. So we just found out the one method, which is a structural light scanning method, that is emits a structural light to the surface, and camera is going to just detect the distorted pattern of those structural light. From there, you should be able to get the point cloud of the surface. So after that, by using photogrammetry, the software should be able to combine or build a 3D model out of it. So what we used was having the 6 microns of the resolution. So this is kind of example that we just got from the 3D scanner. So part of the research project was to construct a database for the local aggregates. So we just collected about the 450. We just collect the 5 different type of aggregates available in the Western Massachusetts, and then we just pick it up the 450, and we just finish the scanning about that one. So we plan to share those 3D models to the public somehow. So then, as long as you are interested in, then please let me know. Then I can just share the whole 3D model of the local aggregate. But anyways, once you get it, then it's not really surprising. I mean, you can just measure the morphology parameter, and then I just plot it according to the DCIS. So there is a diameter for circumferential sphere. So somehow there is a dependency about the size. So so that means that the aggregate is going to be bigger. Somehow there is a tendency to be more angular. However, by using those cloud data points, it's really hard to say that there is a clear the correlation or not. But anyways, that is something that we are just working on. So in the parameter, actually the which value of L is going to be used is going to be quite important. So, I mean, the project itself just saying that we just have to construct a database of it. However, if you're going to just connect this one to the mixture design, somehow we need to carefully think about which the character's length is going to be used. So as long as the mixture design is going to use a lot of information about the sieve test data, that somehow we just thought about the circumferential diameter is going to be one good option for it. But actually, like I said, the marble M factor is not only factor. If you want to connect the surface area and the whatever diameter, and C1 at the first figure can be 3D morphology parameter. If you want to connect the volume and the diameter, C2 can be another one. So anyways, all the power laws can be connect one value to the other. From there, you should be able to get whatever parameters you are interested to play with it. So that is about the individual particle morphology. And then I'd like to just introduce. So if you're going to just really think about the concrete mixture, it has a group of the particles. So even if we were able to characterize the individual morphology of the particles, still we need to know about the group morphology parameter. So there might be many ways to do that. However, this is kind of our proposal. So as long as you have the volume, you should be able to get the volume and the ratio, surface area and the volume ratio of the plane. Somehow you should be able to get those kind of line. So as long as all the shape of the particles are exactly the same, the slope should be exactly equal to -3. However, depending on what kind of shapes are mixed, those slope can be smaller than the -3 or even greater than -3. So I just briefly mentioned about if the absolute value of the slope is less than 3, then that means that the smaller particle is going to be more angular. Otherwise, it's going to be the other way around. So let me just, because I don't have much time, so let me just finish with this slide. So actually, once I just try to use this method, the scanning per particle takes about half an hour. So that is quite the time-consuming procedure. Even if a structural light scanning method is going to save a lot of the time as compared to other scanning method, but still it takes time. So what we are planning to reduce the time is that we anyways built a database about the 3D model, and then we are able to somehow build the morphology parameter the base by using the machine learning. So what we are just right now doing is that we are just training the algorithm based on our the 500 the particle database, and then by using that, if you just bring your phone or pad and taking photo of the field aggregate somehow, you should be able to just get the morphology somehow. So we are now in the kind of the calibration of those algorithms right now. So thank you very much for your time. And if you have any questions, please let me know.